Welcome to Homework Lib.
So in this question, in part A, we are told that the number density of an excited state versus the ground state can be found by the Maxwell-Boltzmann distribution. So the ratio would be e to the negative the energy difference, so energy of the excited state minus energy of the ground state over kT. And given this, we want to prove that the energy of the L state over the energy of the ground state is a certain expression. So let's find it by just working this out. We had the energy of the L state over the energy of the zero state or the ground state. So it is supposed to be e to the negative the energy difference. So we know that the energy of any excited state is given by h squared L times L plus 1 over 2 times the moment of inertia. So when it's L, this is this expression. When L equals 0, the total energy will be 0. So when we find the difference of the energy, we are going to get h squared L times L times L plus 1 over 2I kT. So if we compare this to the form that we are hoping to prove, we see that we're almost there, but we also need a 2L plus 1 in front. Why is it that way? Because for each element, for each level L, there are a lot of different degenerate states. And for each degenerate state L, we have for each energy level L, we have 2L plus 1 possible degenerate states. And for each of the possible degenerate states, we have this many possible numbers, this many electrons in that state. So when we need to find the total state, we find the number of electrons in each state times the number of possible states that all share this energy. So then we can compare our answer to the answer that we are trying to prove, and we see that this is the same expression. So two things here. One thing is that we need to prove that we need to plug this in, that this is the expression for the excited energy. It's h bar squared L times L plus 1 over 2I. And then the second thing is we need to note that there is a degenerate state over here. So once you can properly plug in or explain these two elements, you will be able to prove that this expression is valid. So that is for part A. Let's look at part B. Part B says we want to determine this ratio for a gas of carbon monoxide molecules at 300 K carbon monoxide. And we want to do it for L equals 1, L equals 2, L equals 10, L equals 20, L equals 20, and L equals 50. So that is actually quite straightforward. We just plug L into all of those expressions. So I am going to do the first one, and I will leave it to you to do all the rest of them, but I'll write out the answer because it's the same formula. So for EL equals 1, let's do it in steps. For L equals 1, I will actually use a new page and I will write down this expression. I have NL over N naught equals 2L plus 1 e to the negative h bar square over times L plus 1 over 2IKT. Actually, I'll make a table over here for L equals 1, L equals 2, L equals 10, L equals 20, and L equals 50. So L equals 1, let's first find out what is L times L plus 1. L equals L times L plus 1, that's this part. Here it's equal to 2. This is equal to, actually, let's just do L times L over 2. This is 1. This is 3. This is 55. 20 times 21 over 2 is 210. And last one, 50 times 51 over 2. So that's 250 over 2. And this is equal to 1275. All right, so given that, we can find out what is EL. So I am going to do this for the first one. First one, EL is 1 times h bar squared over 1.449 times 10 to the negative 46 meter squared. So this is just the moment of inertia for carbon monoxide. I did not calculate it here because this question actually asks us to refer to example 42.3, and this number is given by 42.3. So this is 7.67 times 10 to the negative 23 joule. We can do the same calculation for all the following ones. But I can also do E over KT, in which case I am actually going to put in the denominator a couple other numbers. K is 1.38 times 10 to the negative 23, and T is, we are told, times 10 to the negative 23, and T is 300 Kelvin. So if we do that, then instead of just the energy, we are going to get the energy in terms over KT. This is 0.0185. Okay, and I can probably do the same thing for everything else. For the next question, for L equals 3, this turns out to be 0.0556. For L equals 10, we get 1.02. For L equals 20, we got 3.89, and then L equals 50, we have 23.6. Okay, so EL over KT is what we found in this here is we found this part in the exponential order. That's this column. So we can see that the larger it is, that means the smaller this exponential term is going to be because it's negative, this number. Okay, so now let's find the total energy. NL over N naught. So in first case, this is going to be 2L plus 1 is 3. So it's 3 times e to the negative 0.08 5, and this is equal to 2.95. So this is a ratio. Second case, we have 5 because 2L plus 1 is 5 times e to the negative 0.0556 equals 4.73. Third case, 21 times e to the negative 1.02 equals 7.57. Fourth case, 41 times e to the negative 3.89, this is equal to 0.838. And the last case is 101 times e to the negative 23.6. And this is equal to 5.69 times 10 to the negative 9. So why do I need to make this huge table? It's because I want you guys to observe this last column. I'll make the column a little bit clearer. This is the last column. And this is the final answer for all the 5. So if we observe this column, we see that the ratio initially goes up. It goes from 2 to 7. It increases. But then it decreases to very small. So this is related to part C. Part C says that if you look at the ratio, it first goes up as L increases, but then it goes down. And part C wants us to explain why. And how do you explain why? You can explain why by observing this table. So what happens? If we look at the energy, if we look at this term is exponential, it's getting larger, 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 larger. So that means that this exponential term is getting larger. It's getting actually smaller as L increases because this is a negative number. So the larger the thing in the green circle is, the smaller this term is. So that means the individual energy carried by each level decreases as L increases. But if we look at here, there is this other thing because there are a lot of degenerate levels. So if we look at the last column, at first we have 3 times this energy, then we get 5 times this energy, then we get 21 times this energy. So what happens is that even though the L that determines even though the individual amount of energy carried at each state gets smaller, there are more degenerate states as L gets larger. So for the first 3 states we calculated, we see that even though the amount of energy carried by each state decreases, we went from only having 3 states to having 20 states. So the degeneracy actually outweighs the amount of energy decrease. So the total ratio still increases from 2.95 to 7.57. However, we see that this decrease is an exponential decay as opposed to the increase. 2L plus 1 is a linear increase. And we know exponential things are just they increase or decrease faster than linear things because exponential is a higher order than linear. Because of that, when the number is small, the linear might wins over exponential. But as L gets larger, eventually the exponential is going to be the more significant one. So as L increases, the exponential gets so small that the degeneracy number, even though we have 100 states, the total number is still going to be smaller than if we only have one state, L equals 1, because the exponential decreases so much faster than the linear thing. So that is the explanation. Why the number ratio first increase and decrease. It increased because we have more degeneracy states, and it decreases because as L gets larger, the number of electrons in each individual states gets smaller.